We begin with a wire loop suspended in the dark. A magnetic field clicks on, and the loop snaps into a sudden 90-degree twist. Summing the magnetic forces on each arm shows a total of 0. Every leftward pull is met with an equal rightward tug. Yet the loop isn't just sitting there, it's spinning. On this rectangular diagram, the magnetic force pushing the top arm up is perfectly cancelled by the force pulling the bottom arm down. The same applies to the left and right sides. In a uniform field, there is no net linear force. While the forces cancel, they are applied to different points. Because these lines of action don't overlap, they create leverage. This specific arrangement is known as a couple. It is a pair of equal and opposite forces acting along different lines, which results in a pure rotational movement without any lateral shifting. This behavior shows the transition from linear electricity to rotational magnetism. It demonstrates that the impact of a force depends entirely on where it is applied to the object. To calculate the strength of this twist, let's look at the loop while it's parallel to the magnetic field lines. We'll label the four arms A, B, C, and D. Charges must cross field lines to generate magnetic force, so these parallel segments experience 0 force. Arms A, B, and C, D cut directly across the field, experiencing maximum opposite forces. F1 pushes down into the plane, while F2 pulls up out of it. Viewed from the side, these two forces act on opposite ends of the loop's width, A. This width becomes the physical lever arm for the rotation. Torque is the product of the force and this distance. Since the force on the wire is current times length, and we are multiplying that by the width, we are essentially calculating the area of the rectangle. This is our first result. The torque, tau, is the product of the current, the area of the loop, and the magnetic field strength. In this entirely flat orientation, the wire loop converts the uniform magnetic field's pressure into its maximum possible mechanical torque. Once the loop begins to turn, we define the angle theta between the magnetic field and a line perpendicular to the loop's surface, called the normal vector. As the loop rotates, the vertical forces remain the same, but the horizontal leverage distance decreases. Our lever arm is no longer the full width. The effective distance is now determined by the sine of the angle theta. We update the equation to account for this. Torque now equals current, area, and field strength multiplied by the sine of theta. By grouping current and area together, we defined a property called the magnetic moment. This single value represents how much rotational pull an object will experience in any given field. This relationship explains why the twist feels strongest at the start and gradually weakens as the loop turns towards its final position. The rotation continues until the loop's normal vector is parallel with the field lines. At this point, the angle theta is 0. Because the sine of 0 is 0, the torque disappears. The forces are now pulling in a straight line through the center of the loop, locking it into a state of stable equilibrium. This same principle guides a compass. The needle is a magnetic dipole that oscillates until it sheds its torque and aligns with Earth's magnetic field. From a giant wire loop down to a single electron, any magnetic dipole is subject to this interaction. They are all driven to reach the orientation where the torque acting on them vanishes. The initial twist is the physical process of seeking that alignment. Torque persists until the loop's magnetic moment is synchronized with the external field lines. This predictable relationship between current and torque is the basis for the moving coil galvanometer, the standard instrument for measuring small electrical currents. Inside, an iron core and curved magnets create a radial field, ensuring field lines strike the coil at 90 degrees. As magnetic torque twists the needle, an internal spring provides counter-torque until the forces reach a steady balance. In this equilibrium, the physical deflection of the needle is directly proportional to the current flowing through the coil. The math of the twist becomes a readable value on a scale. By isolating this rotational behavior, 19th century physicists turned an abstract interaction into a calibrated tool. It provided a reliable way to translate invisible magnetic forces into the standardized measurements used in electrical engineering.